Here we have our second basic example of how to work with work and energy. Power will come later. And if you look at this and say, well, wait a minute, I saw something like that on the first video, video number 1. And yes, you're right, except there's one big difference. In this case, the force is not pushing horizontally against the block, it's pushing at an angle. In this case also, we don't have any friction between the block and the floor. So if the distance or the displacement is 50 meters, the mass is 5 kilograms, the force is 100 newtons, and the angle is 30 degrees, what is the work done in this case on that particular block? Well, what we're going to do is we're going to do this in two different ways. First of all, we can go ahead and use the straightforward definition of work. We can say that work is equal to force dot displacement, and I guess my pen is a little dry here. So these are vector quantities. So this is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. So this is equal to a force of 100 newtons times a displacement of 50 meters times the cosine of 30 degrees. And then with a calculator, let's find out how much that is. So that would be 5,000 times the cosine of 30 equals 4,330 Newton meters. And remember, a Newton meter is a joule, so this is 4,330 joules. That's the work done moving that box 50 meters like that. Another way of looking at it is as follows. You can say, well, this force can be divided into two components. We can divide it into a horizontal component and into a vertical component, F sub y. And then you realize that if we look at all the forces acting on the mass here, we have the force of gravity, which is pushing down mg, and then we have this vertical component, F sub y, pushing down on the block downward as well. So now we have a normal force pushing back, and the normal force here will be the sum of the weight of the block plus the component of the force pushing the block, which is downward, plus the F sub y. And of course, F sub y can be found by taking the F times the sine of the angle, because it's the opposite side to the angle. So we can say this can be written as the weight, mg, plus the force times the sine of the angle theta. Remember that this is opposite to the angle, this is the force, so we know that's the sine of that angle theta. All right, but notice if there's no friction here, friction is 0, that means that this normal component does not give you any friction force, which means that the entire work done is simply used to give the block energy. All of the 4,330 joules were given to the block in terms of energy. So when the block has reached a distance of 50 meters, the block will now have 4,330 joules of energy. And what kind of energy? Well, it's actually kinetic energy because the block did not gain any height. Potential energy, in this case, would be gained if the block had gained altitude or height. But since it's all on a flat surface, all of that 4,330 joules will have been converted into kinetic energy. So by the time the block gets over here, the block will now have, so the kinetic energy of the block at this point will be 4,330 joules, meaning all this work was converted to energy. None was lost by overcoming friction. And that's how you do that.